Hello everyone, my name is Ziteng. I'm a PhD student from Georgia Tech, and today I'm going to present my recent paper on fully verified instruction scheduling. And as you may be aware, that there has been lots of advances on compiler correct list and verification. The goal is to set 100% correct list guarantees. 100% guarantees. And CompCert is one of the most representative examples. It established the formal semantics and syntax from the source C level to target assembly levels, and implemented compiler passes and optimizations, and fully proved the correct list and preserved and proved the semantics preservations between those translations. And the current state of CompCert is not yet perfect. I think one of the most important problem is it cannot reorder the instructions. That means you can only do in-order translations, but not out-of-order translations. And it is also called instruction scheduling. So the motivation for the compiler level instruction scheduling is that different order of instructions may cause different cycles per instructions during the on different microarchitectures, and some microarchitectures does not support out-of-order execution. That means the responsibility is passed to the compilers. If we can reorder the instructions properly, it may have less CPI. So the challenges to formally verify the instruction scheduling is that the dependence inside the basic block is complex. That means the previous framework in CompCert, which requires a lot-step simulation relations, that means the state of program execution is matched step by step, which is also called a lot-step simulation, that is no longer satisfied. The program state will only be matched at the start and end of the basic block. Even I mean, if we are considering the situation intra-block scheduling, and it will be much more complex if we are considering inter-block scheduling. So the previous work on this problem, they only provide the solutions on verified translation validations. That means they verified the validator, not the algorithm itself. And the motivation is to do a full verification, which is our work. And it potentially requires more difficult develop time, and it may have much less flexibility. But the motivation is, if we can finish this, first the algorithm can be fully trusted. Next, and also the compiler time overhead can be reduced, because if you are doing the translation validation during compiler time, you have to check each input and output for every compiler cases. And so this graph shows the differences in the Philo theorem we want to prove. The previous work, the Philo theorem of the previous work, it has strong assumptions in that during each compiler cases, the input and output pass the validator check. But our goal is to just prove the algorithm is correct. So if the compiler generates a result, the result is already correct. It do not have to pass any other checks. And this work is established based on the previous CompCert work, and we picked the proper intermediate representations and implemented the specific instruction scheduling algorithm on that path, and use our theory to prove the correctness of it. So in the next few pages, I'm going to introduce my logic chains, which consists of 5 parts, about how I formally proved and keep the formal proof lightweight. So the first part, which is the core idea of our paper, is using a very simple property. We named it swapping lemma. So the property said if two lists are a topological reorder, of each other, assuming we already have some relation on them, and if two lists they consist of same elements, and they are a topological reorder of each other, this reordering is equivalent to a series of swappings, a series of swapping that only swaps adjacent independent elements. You can look at the right figure. And the second component of the logic in the logic chain is to define the syntax level instruction scheduler, syntax level valid instruction scheduler. So what is syntax level valid? That means the scheduler preserved the syntax level dependence relations. The syntax level dependence relations means we define it to have dependence if the syntax of the register name is matched, or if they are both addressing the memory and one of them are right. One of them are right operations. And the memory definition is a strong dependence. And the third component is, from the previous two, we get a conclusion that we can decompose a valid scheduler. That means if a valid scheduler preserves the syntax level dependence relations and is a topological reorder on the basic block, then such reordering is equivalent to a composition of finite sequence of smaller compiler passes. And the smaller compiler passes only swaps one pair of instructions inside one basic block. And just look at this graph. If we have an input basic block L and the actual scheduler we implemented scheduled the basic block into another block SL, then such scheduling, as long as the SL still satisfies the dependence relation, this schedule is equivalent to the finite sequence of swapping. Then the third component is already existing result is the transitivity of semantic preservations. So in the whole project of CompCert, the final goal is to prove the backward simulation between the C program and the assembly program. But due to the deterministicism of assembly program, the backward simulation can be derived from the forward simulations. So if we want to prove one path of CompCert, we only have to prove the forward simulations. And the forward simulation is transitive. So that means if a path is equivalent to a composition of a finite sequence of smaller paths, as long as all of the smaller paths preserves the forward simulations, the bigger paths also preserve the forward simulation. So I think now it's obvious that what we want to prove finally. We want to prove the semantic preservation of the smaller paths, which we named simple swappers, that only swap two adjacent but independent instructions. And here's the only places we will go into the semantic details on the execution of a program. The previous part only involves syntax. And so briefly speaking, the semantic details we lead to reasoning on different cases of instruction pairs, and prove that after 2 steps of executions, the program state still matches. And connecting all the 5 components, we can get the full picture of how our proof idea is constructed. So if we have a list of base instructions and get a schedule that preserves the syntax level dependence, we can prove the forward simulation of the scheduler by proving that it is equivalent to a sequence of little swappers, and little swappers preserves the forward simulation. And according to the transitivity of forward simulations, the fellow scheduler preserves the semantics. So what did we get here? We get a general framework on how to prove instruction scheduling algorithm. The result is, for typo. The result is as long as the syntax dependence is preserved, the semantic dependence is preserved. So this conclusion is once for all. As long as we implement it in in an interactive theorem prover, every new algorithm that trying to reorder the instructions inside baseboard can reuse our previous formalizations. And of course, those framework is already formalized in the proof assistant code based on the CompCert framework. And so we also did the proof on a concrete list scheduling algorithm using this framework. So the list scheduling algorithm is very simple. That you give you a basic block, we build a dependency graph based on it. Then we iteratively pop the independent load from the dependency graph and append them on the end of the already scheduled instructions. And during the picking, we may have multiple correct choice. So we may also need heuristics to ask which one to pick is the best. And this heuristic does not affect the correct list, but it only affects the performance of the compiled program. And the basic idea to prove the syntax dependence preservation is basically prove that it preserves an invariant during such iterative picking. And it says that the already scheduled list and the remaining dependence graph, they are exclusive from each other, but the union of them are exactly the same as the original list. And the already scheduled list L it always keep the double sorted during such scheduling, during each step. But the concrete formalization has more, slightly more difficult than this slide. But everything is formalized and checked in code. And we also incorporate it into CompCert project and make it possible to just compile a C program into some targeted targeted machine program. So we can do an evaluation on this project on two views. The first view is proof engineering. So how lightweight is our work? So we are coding the formal proof using the same coding style as the CompCert or previous work. And you can see that we have similar amount of lines of proof codes, but our fellow row is slightly different. But it's all around the thousands of proof codes for the scheduling algorithms. And we also did some simple evaluation on our concrete list scheduler's performance on the compiled program based on the RISC-V hardware architecture. And the conclusion is our scheduler did have some performance on the Polybench benchmark. So the summary of this paper is we did the first step on how to verify the instruction scheduling passes formally and did a full proof, not translation validations. And also we have I believe we have multiple levels of flexibility. We are flexible on algorithm changes. When you are changing the algorithm, we only change the proof that it preserves the syntax dependence. We don't have to touch the proof on semantics again. The next level of flexibility is the heuristic is flexible. So if we are doing the optimization on the different scenario, we may need to change the heuristics, but we never need to touch the proofs. And also the implementation is almost machine independent. Only like 40 lines of core code is different between the x85 architecture and the RISC-V architecture. The other proofs are exactly the same. And you also may need implement the different heuristics for different architectures. And the future work, and talking about the future work and also the limitation of this work is, first we are treating the first step on intra-block scheduler, low previous sort did even for this simple task. But the harder task is how to verify in the inter-block scheduler. And we may also need a weaker definitions on the memory dependence, because that requires extra work on LSLS or memories. And generally speaking, we also may consider in multi-level parallelism for verified compilers at larger levels. This project, I believe, is on the instruction level parallelism. But we may also need to consider in the data level parallelism or task level parallelism. For task level, we may consider in the loop parallelism for sequential programs. And if we can try to explore those areas, we may bring CompCert to the O3 and even O2 or even O3 level optimizations. And that would be all my presentations. Thank you.
Cool talk, thanks. So on the performance benefits that the slide, like, yeah, that one. So how does this speed up compare to in an unverified scheduler? Or like, do you know how this compares to an unverified scheduler if you take out, instruction scheduling? Are these performance benefits similar to the performance benefits you get if you, take out or?
We didn't do experiment on comparing to the previous, because the previous work is on different architecture, and it's on a very I think it's something called Charlie KVM, and our project is targeting on Richard 5, so it's hard to compare. But the speed up, I think the speed up of their untrusted scheduler is faster than this verified, because they can do much more code on and development on the trusted scheduler, and they don't need to touch the proof. This is what I talked about, the flexibilities for the trusted scheduler. If we want to do more optimizations, we may need more theories on the proofs.
Thank you.
Thanks, great talk. One of the first slides, you had a kind of comparison between this work and the full translation validation. And I think the very first slide, yeah, it was like the second slide. It's fine. I mean, feel free to. There we go. Yeah, we just passed it. So I think there's a row there where they're talking about the performance of both, and I'm ready to believe that like an extracted OCaml function is faster than asking an external, instruction scheduled or do something. But do you have any sense for what the delta is in that third row?
Third row?
The overhead?
Yeah.
Yeah, I'm just curious what, you're saying the verified translation validation takes more time to compile. Yeah. I'm curious if you have any sense for what the actual difference is.
So we actually did some comparison on our papers, but didn't take it on the slides. I think so. We compile the modified CompCert of the previous work, and I think they may have like 2 times of slower compile time if they are doing the if they are doing the runtime validations.